action. Hey, everybody. Today we're going to talk about some of the things that you need to be carrying from Chemistry A over with you into Chemistry B. Specifically, today we're going to focus on navigating the periodic table, knowing where certain things are and how to tell certain things about elements within the periodic table, and also some of the important trends that you should be aware of that you learned in Chemistry A. So let's get started. First of all, I want to go through the different groups in the periodic table and tell you some information about them. So remember that the groups are the vertical columns in the table, and each group has, depending on what group things are in, it can tell you a lot about that particular element. So we're going to go through each of the groups and talk about what their name is, if they have a special name, how many valence electrons elements in that group would have, what kind of ionic charge those elements would form, what their oxidation state would be, and what a Lewis dot structure of the first element in that particular column would look like. So we'll start with column 1 right here. These are called the alkali metals, which I'm not going to write here because it would take me forever to draw that with my mouse, but they're the alkali metals. Now I will start drawing. Let's go with teal. Yeah, let's go do that today. All of the alkali metals, everything over here in column number 1 is going to have one valence electron. It means they have one electron in their outermost highest energy valence electron orbital. And remember that everything is trying to achieve the octet rule. So when it's going to react with some other element, it's going to act in a way that's going to get it to achieve an octet, which means a full outer valence shell of electrons, or 8 valence electrons. And there's two ways that that can be done. First of all, an element could either gain electrons up to 8. So in this case, the alkali metals could gain 7 electrons, or they could simply lose the valence electrons that they have. And by losing those valence electrons and emptying the outermost valence shell that they have, that shell just disappears, and the shell below it is already full and already has an octet. So you can lose all your valence electrons. An element can lose all its valence electrons or gain enough to get up to 8. So if it only has one valence electron, like everything in column 1, it's going to lose that one electron because that's easier than gaining 7. And if you lose a negatively charged electron, you form a positive 1 charge. So everything in column 1 forms a positive 1 charge. That is also the oxidation state of everything in column 1. Oxidation state at this point, you can think just means the same thing as ionic charge. It's really, oxidation really has more to do with a certain type of chemical reaction we're going to talk about called oxidation reduction reactions. And that's where charges can change in the process of a chemical reaction. But if you're just looking at something with a charge and you ask what oxidation state it has, it's the same as its ionic charge. Now, the Lewis dot structure of something with one valence electron, let's say lithium is an example of the top element right here in group number 1. If it has one valence electron, it's just going to be one dot. Whoa, it's a big dot. One dot at the top there. All right, let's move on to group number 2. These are called the alkaline earth metals, and everything in this column has 2 valence electrons. You might be starting to see a pattern here, and that's very intentional on the periodic table. Patterns are what it's all about. Everything in that column has 2 valence electrons. It's still going to be easier for any of the alkaline earth metals to lose their 2 electrons rather than gain 6, which means that everything in this column will form a +2 charge. Whoa, I'm new to this. And that means that its oxidation state is going to be +2 as well. Now, the top element in group number 2 is beryllium. And beryllium, if it has two, I'm going to have to stop doing this because it's going to get too hard, has 2 dots just like that. Boom, boom, representing the 2 valence electrons. All right, moving on to groups 3 through 12, this big chunk in here. This part of the periodic table has a couple of different names. It's called the D block, and that refers to certain types of valence, not valence, certain types of orbitals. This is also called the transition block. So these are the transition elements. That's what I would write down there for the name. And everything here actually kind of varies a little bit. This is where it gets a little tricky. These transition elements don't always have the same number of valence electrons. Generally, it's 2 as a general rule, but it can vary. And in fact, a lot of those elements can have different amounts of valence electrons at different times. Iron, for example, could have 2 valence electrons, or it could have 3 valence electrons, just depending on the situation. So I'm actually not even going to write anything in here and just say that this also varies. Can I write it? Varies. Sure. And we'll move on. Group number 13, right here. No special name, right? It's the group with boron at the top. We can call it the boron group, I guess. And everything here is going to have 3 valence electrons. So here's where our pattern continues. If you just imagine skipping over, jumping this gap, jumping over this gap from the alkaline earth metals to the boron group, everything here has 3 valence electrons. It's still going to be easier to lose those 3 valence electrons rather than gain 5. And so when it does that, it's going to form anything in that column will form a +3 charge in terms of ionic bonding or any other charge situation. So that means the oxidation state will also be +3. And let's say that we want to draw the symbol for boron with 3 valence electrons. It'll look like that. Now, group number 14, the group that starts with carbon, the carbon group. This is where it gets interesting because everything in this group has 4 valence electrons. Now we're halfway between 0 and 8, right? If something has 4 valence electrons, does it gain 4 or does it lose 4? And the answer is it could do either. So depending on the situation, anything in this column could form a plus or minus 4 charge, which means it could form a plus or minus 4 charge for oxidation state as well. Carbon with 4 valence electrons would have a Lewis dot structure like that. Remember, drawing Lewis dot structures, you add 1 dot every 90 degrees, starting at high noon or starting at the top and going 90 degrees each time. And pretty soon here, we'll find out what happens when you've gone all the way around and you have to add more. Let's go to column 15, group number 15. This is the nitrogen column. So it starts with nitrogen at the top. Everything here has 5 valence electrons. And if it has 5 valence electrons, ooh, that means that now it's easier to gain electrons, to gain 3 rather than lose 5. And in that case, it would form a -3 charge, which means it would form, whoa, I got to do something with my mouse here. A -3 oxidation state. And that means that the Lewis dot structure of, whoa, okay, nitrogen with 5 valence electrons would look like that. Once we've gone all the way around, we just go back and we start adding dots next to the ones that already exist. This is going to get messier before it gets cleaner, everybody. Hold on with me. Now, group number 16, the group that starts with oxygen. Oxygen is at the top of this group. Group number 16 has a special name that not many people know and no one uses, but I just think it's a great word and everyone should know it. They're the chalcogens. The chalcogens. And they have 6 valence electrons. That means that it's easier for them to gain 2 electrons and form a -2 charge than to lose 6, which means they'll form a -2 oxidation state. And if it has 6 valence electrons and we want to represent that in a dot structure, it would look like that. Second to last column, these are the halogens. The halogens. Halogens. And they have 7 valence electrons, which means it's going to be easiest for them to gain 1 electron. Remember, electrons are negatively charged. So if you're gaining electrons, you're gaining negative charges. That's kind of the weird mental shift you have to make. You're gaining things, but it's becoming more negative or whatever. So What's the halogen at the top? Fluorine. That's right. And if fluorine has 7 valence electrons, it'll look like 1, 2, 3, 4, 5, 6, 7. I already. I'm losing it, you guys. Now we're on to the last group, the noble gases. These are special because they already have 8 valence electrons. They have an octet naturally. They don't have to do anything, which means that they're not really going to form ionic charges. They're not going to really have oxidation states. And they have a beautiful symmetrical electron dot structure where every possible place for an electron is full. So there you go. You should be able to do that from memory. I should be able to look at any element on here and be like, this element right here, how many valence electrons does it have? And what kind of charge is it going to form if it forms an ionic compound? And how would you draw the Lewis dot structure for that element in its neutral form? And not anyway, you would be able to do all of those things. Let's move on. Whoa. Am I really going to have to erase all this? Oh my gosh. Okay. Okay. I'm sure this is what you signed up to watch when you turn this video on. You can tell I'm figuring this whole system out. I should have left him there. Oh well. Now let's talk about something new. I'm going to disappear for a second. Ah! One of the most important things to know about the periodic table in just looking at elements and kind of thinking about how they're going to interact with one another is you need to know where the metals are, where the metalloids are, and where the nonmetals are. I'm actually going to start with the metalloids because that's kind of how you know it all. You might remember that there is a special staircase that you can draw along the periodic table right here. I started out really well, and then things kind of went downhill. And everything that hits that staircase, other than aluminum, is a metalloid. So aluminum is actually a metal, but everything else, all these are the metalloids, which means metallish. They have kind of metallic properties. They have kind of non-metallic properties. They're kind of a in-between group between metals and non-metals. Now, everything to the left of that, all of these, except for hydrogen, but everything to the left of that, including this F block down here, these are all metals, right? All metals, and that includes these ones that I didn't touch with the cursor here. And that means that everything to the right, all of this over here, these are the nonmetals, and hydrogen is also a nonmetal. Now, the reason that you need to know that is going to come up in the next lecture that I record, which is how to do compound nomenclature, right? Ionic and covalent bonding. Different combinations of things will bond in different ways, and it has to do with electronegativity differences, but there are some hard and fast rules that you can know about whether it's two metals or two nonmetals or a metal and a nonmetal that will help you to determine what kind of bond is going to form and what kind of compound is going to form, and therefore how to name that compound and write formulas for that compound. But we'll get to that. That's another lecture. Okay, I want to come back. Hi, I'm back. Let's move forward. Oh my gosh. Okay. Let's get rid of this. Oh, there's a wipe screen option. I'm sorry about earlier. I can actually get rid of everything. Now I know. The last thing that I want to cover really quickly is some trends in the periodic table that you should be aware of. Atomic radius refers to the size of an element, and you might remember this from chemistry A. As you go from top to bottom on the periodic table, atomic radius increases things get bigger, which makes sense because the atoms are getting bigger, right? The periodic table is listed from lowest atomic number or lowest number of particles to highest number of particles as you go from left to right, top to bottom. So the things with the most pieces are at the bottom and the things with the least pieces are at the top. So it makes sense that things get bigger as they go from top to bottom. However, from left to right, the opposite is true. Even though as you go from left to right across a period in the periodic table, you are gaining particles. Things over here have fewer protons and electrons and neutrons than things over here. The atomic radius, the size of the atoms, actually decreases. And as you might remember, that is due to something called Coulomb's law and coulombic attraction between charged particles. Because as you go from left to right across the periodic table, yes, you are gaining technically more mass and you're gaining more particles in those elements, but you're also increasing the electrical interaction between those elements. So as you go from left to right and you gain more, for example, protons in the nucleus, you are increasing the positive charge of that nucleus, the magnetic property of that electrically charged nucleus. And so with more magnetism, with more positive charge, that nucleus is going to pull electrons more strongly towards it. So even though there's more protons and probably more electrons in that atom, it's going to, the nucleus is a stronger magnet, you can think. And so it's going to pull the electrons closer in. So the atoms are actually shrinking as more protons are added to the nucleus. So you might think, well, okay, why isn't hydrogen the biggest element and things just get smaller from there? The reason that things get bigger going down, if you look at atomic sizes, they actually kind of decrease, 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 and then when you get to the end of a row, it jumps back up to bigger than ever. And that's because you're adding the next orbital level. You're adding the next valence shell that's going to start to fill in. And so you're kind of adding this whole new playground. You're doing a big renovation, expansion of what is possible and where particles can go. And so the atom's going to jump up in size there. That didn't work. Now, you also need to know a little bit about ionization energy. Ionization energy is the energy that it takes to ionize something. And if you remember, an ion is a charged particle. And so ionization energy means the energy required to remove an electron from an atom, therefore giving it a charge. So atoms are holding on to their electrons, right? But it is possible to tear those electrons away from an atom. The thing is, it's going to take a certain amount of energy to overcome the pull that the atom has on those electrons and rip them away. And that's what ionization energy is. And it follows the opposite trend from atomic radius. As you go down, ionization energy decreases. And that's because the atoms are getting bigger and bigger and bigger. And so, again, it goes back to Coulomb's law and the interaction between positive and negative charges. But as an atom gets larger, the distance between the positively charged nucleus and the negatively charged electrons that are attracting one another increases, right? The atom is getting bigger, and so the distance between things is increasing. And what happens if you take two magnets and you move them further away from one another? They don't have as strong a pull on each other. And so because there's less strong of a pull on those electrons from that nucleus, it's easier to take the electrons away. Ionization energy, however, increases from left to right due to what's happening with the atomic radius. As the nucleus gets more protons and becomes a stronger magnet that's pulling on its electrons more strongly and pulls those electrons closer in, and the atom actually shrinks in size, the combination of the decreased distance between the positive and negative charges, as well as the increased magnitude of the positive charge, makes it really hard to remove the electrons from the atom. So the ionization energy required to do that increases. One more. Stick with me. Electronegativity was the other important trend that we covered on the periodic table. It's important to note that there are many other trends that you could talk about and track on the periodic table, but these are some of the most basic and most important ones that you need to know. Electronegativity is kind of related to ionization energy. Well, it's very similar, but it is its own distinct thing. Electronegativity is the pull that an atom has on electrons. And this really is most important when you're thinking about the pull that an atom has on electrons of another atom when it comes to like bonding and things like that. So electronegativity, the pull with which an atom attracts other electrons to itself, follows the same trend that ionization energy does. It decreases going down and increases going from left to right. And again, this is due to Coulomb's law. And it's really kind of ties back to atomic radius and what's happening with the size of the atom. As the size of the atom gets bigger, there's going to be more space between the positively charged nucleus and whatever electrons that nucleus is trying to attract. So it's going to have less pull on those electrons. As the atom gets smaller and the protons in the nucleus increase and there becomes more positive charge in the nucleus, that nucleus is going to pull electrons more strongly towards it. So electronegativity is going to increase from left to right. And there you have it. That is a basic overview of some of the most important stuff that you need to take away from Chemistry A in terms of the periodic table and how to navigate it and what might come up in the future and what you should know about elements in the periodic table. So until next time, take it easy and have a great one.